So we can integrate anything. So 5.3, we're going to do exactly like we did for problem number 25. All right? We're going to do a lot of it. But before we do that, I want to write down some rules of definite integrals. These are equivalent statements, and the first one is this. It doesn't matter what A or B is, these are some convenient properties, and we used one of them for problem number 25. What do you notice on the screen? Yeah, what I did is I flip-flop the lower and upper limits. And if we choose to, there'll be applications where you might want to flip-flop those. If you flip-flop them, you can. It's just remember that you have to toss the negative sign in the front. Okay, so that's one equivalent statement. I don't know if we'll do the proofs for some of these identities today because we don't have enough time. But you should write these down. This is the order that they teach it in the book. All right, so hey, what do you think this is? I'm going to evaluate f of x, with respect to x from A to A. What do you think that is? Think of a graph. What do you think that is?
1.
No?
0.
Yeah, it'd be 0, right? Because if we do any approximation that we do, delta x is 0, which is not good, right? So if we do like a rectangular approximation, we're basically saying what is the area of a rectangle with the width of 0? Well, it's 0. Okay? Why?
No, I said it's a line.
Yeah, but a line's one dimension, and we're technically calculating the area under the curve, so you need 2 dimensions. Okay. All right, so let's do another one. What do you guys think this is? I just did this for problem number 25. If k is some constant, like it's a number,
you can throw it in the front.
Toss it to the front. Very good. Someone was paying attention. Toss it to the front. That's really convenient. Because when we go to evaluate these, like we're going to, in this next section, we're going to do like polynomials. And it's a lot easier to like toss the 3 to the front, do all the antiderivatives, and then multiply your answer by 3 at the end. Okay, so we'll use that one a lot. Ooh, this one looks fancy. What about this one? This is kind of similar to the previous one.
Can you take the negative in front?
Yeah, you take the negative to the front because technically what we're doing is we're multiplying the whole function by -1. So you just toss the negative to the front. That makes it easier too. And you can introduce it that way too. So like if I mean that goes both ways. It might be easier for me to integrate something if I factor out a -1, and then once I have the -1, I tack it onto the, I toss it to the front, and then at the end we'll tack it onto the end. This is based on limits. Do you guys have this written down?
Mm-hmm.
Yeah. No?
Yes.
Almost. Yeah.
Well, while you're writing this down, allow me to take a coffee break.
Okay, I got it.
I feel like Jeopardy music should be playing.
Why does yours sound like?
All right, here's another one. Now remember that these are. I don't know if you guys remember this up here. I don't know if you guys remember this or not, but we did similar properties with limits. So these properties, because the derivatives were based on the limits, right? And the integrals are based on the derivatives. The properties for limits are very similar for the properties of integrals. So what do you think? How would I do this? That's going to equal something.
plus or minus?
Yeah, we could do f of x plus g of x or f of x minus g of x. You remember that from the limits and derivatives?
Oh, yeah.
Does that look familiar to you, Alan?
Yeah.
Wait.
Alright, can we do another one? You've got this written down, right?
No?
Wait, I need to get the bottom
It's
part.
in your book on
Wait!
page
Oh my goodness!
285. No, I'll put it back. Hurry up, you guys.
Well, now it's done. Now I wrote it down.
No, it's not. Wait, pause a minute. Pause a minute, okay?
Oh, I understand.
Wait, why is it do that? Oh.
Okay, so what I'm saying is, you're probably saying, Mr. Adams, I don't understand what that means. All right, so what if I wanted to do this? Well, let me do it on another page for you, okay? What if I wanted to do something like this? That's the same as Does that make sense? So when we do a polynomial, I could. She said. Well, if I have a polynomial, there are situations where I might want to break up the function. And if it's a sum of two functions, I can integrate each function separately, right?
Yes.
JP, do you have this written down?
Not quite.
Okay. Let's go to courtesy mode. Does that make sense?
Mhm.
Do you have it written down?
Yes.
Yes.
By the way, I could do it this way, or I could do it this way, or I could what we end up doing is something like this, but we do it in our head. Okay?
What?
You will eventually.
I can't start it in my head.
What else? Oh, this is a good one. This is a good one. What do you think that is? Now let me show you something too. This will help you out. If you're confused, think of it like this.
Is that an A at the top?
Yeah, what's the top letter on the second one?
A, B, B, C.
That looks like a 7.
Oh,
Don't judge me or my penmanship.
An upside down 7.
Look at that. What am I saying? I'm saying that from here, I'm going to take the area under the curve from here to here. Right? And then from here to here, I'm going to take the area under the curve like that. Is there a simpler way to do that?
Isn't it just from A to C?
You guys are brilliant.
I know.
Yep. I just go from A to C of f of x. We'll use that a lot as well.
Yeah.
I'm going to skip the other ones because I'm going to wait till we get to an example. Okay? There's two more, but to get into them, it'll take too much time. Does anybody have any questions about this?
Not yet.
What should you have in front of you when you go to do your homework for this assignment?
Your
Calculator.
nose.
Calculator.
Possibly some
Wow.
These properties.
Are they
Okay.
in the book? Are